Watch a heavy-duty industrial robot in motion. It throws thousands of pounds of steel through the air at high speed and then stops instantly, locking into a precise position with sub-millimeter accuracy. Achieving that kind of rigidity requires the immense torque and high natural frequency of a hydraulic actuator. But fluid power is inherently volatile. You are dealing with highly pressurized oil, turbulence, and nonlinear dynamics. This presents an engineering paradox. We have to take low-voltage, mathematically perfect digital signals from a computer and translate them directly into raw, volatile mechanical force. The primary electromechanical bridge where this translation occurs is the proportional solenoid valve. Getting this valve to behave with exact precision means overcoming three physical barriers. First, magnetic hysteresis. Second, pressure flow nonlinearity. And third, thermal shifting. Achieving absolute mechanical precision requires acknowledging these physical realities. You have to master the signal-to-force pathway through dynamic feedback and aggressive algorithmic compensation. The journey begins at the programmable logic controller. The PLC sends out a digital pulse width modulation, or PWM, command. When current hits the coil, it induces a magnetic field. That field pulls the ferromagnetic plunger, opening the valve. But the reaction is not instantaneous. It takes a fraction of a second for the magnetic field to build to full strength. This is magnetic lag. While that field is building, the physical spool is fighting static friction, or stiction. The spool remains locked in place until the magnetic force builds high enough to break that friction and snap the spool into motion. Combine the electrical lag of the coil with the mechanical stiction of the spool, and you get a phenomenon known as hysteresis. This XY plot shows a nonlinear relationship. Commanding the valve 50% up results in a different position than 50% down. The central gap creates a massive deadband. Micro-adjustments inside this gap fail. The signal is sent, but the spool does not move. To solve this, engineers close the loop directly at the valve. By installing high-speed LVDT sensors, the system measures the exact spool position and forces it to the correct coordinate, overriding hysteresis. But an LVDT only corrects the electrical error. Forcing the spool to the correct position guarantees the opening size, but not the actual fluid flow. To control the fluid, we must look past the electrical solenoid and examine where the pressurized oil meets the physical opening of the spool. The dynamic flow of that oil is dictated by the orifice equation, Q equals CD times A times the square root of delta P. The variable A represents the physical area of the valve opening, the spool displacement we just stabilized. Assuming doubling the opening doubles fluid flow is incorrect. Looking at this quadratic curve, fluid velocity is dictated by the square root of delta P, the pressure drop. As pressure differential increases, flow rate changes exponentially. If the robotic arm picks up a heavy load, the dynamic back pressure in the system instantly spikes, drastically altering the pressure drop across the orifice. The fluid flow rate becomes erratic, even if the valve opening remains perfectly static. Furthermore, circuits often utilize components like counterbalance valves to hold a load in suspension. These components introduce their own back pressure to keep the load from dropping, constantly shifting the delta P across your proportional valve. Because of this shifting pressure differential, locking the valve spool in place isn't enough. Controlling the actual mechanical velocity requires calculating and adjusting for this fluid flow in real time. Fluid flow also introduces a thermodynamic variable. As highly pressurized fluid squeezes through valves, the hydraulic horsepower consumed by fluid friction is converted directly into heat. This line chart illustrates the relationship between temperature and the kinematic viscosity of hydraulic oil. As system temperature climbs, viscosity drops. The thinner fluid easily slips past seals, drastically increasing internal leakage across the entire circuit. This thermal decay shifts the system's physical transfer function. A voltage command that produces smooth movement at 70 degrees Fahrenheit yields a totally different mechanical response when the system hits 150 degrees. If a control system is statically calibrated for a cold morning startup, the thermal shift causes it to oscillate, lag, and fail by the afternoon. To tame these erratic hydraulic and thermal variables, industrial systems rely on a continuous software feedback loop, the PID controller. On the right side of this split screen, the line graph tracks an untuned control system attempting to hit a sub-millimeter target. Without proper tuning, the system violently hunts for the position, overshooting the target line. The first step is the proportional, or P, gain, providing the initial driving force. But fluid has mass. Setting a high P gain forces the system close to the target, but it oscillates aggressively as fluid inertia carries it past the mark. To stop oscillation, we apply the derivative, or D gain, acting as a predictive electronic shock absorber. It calculates the approach rate, aggressively braking the spool to counteract fluid inertia and smoothly flattening the curve before it overshoots. A microscopic gap often remains between actual position and target, a steady-state error caused by internal leakage. To close it, the integral, or I, gain, continuously sums up historical error, increasing output until it perfectly matches the target line. In highly advanced applications, adaptive algorithms constantly monitor the hardware in real time. They automatically recalibrate these P, I, and D gains on the fly to counteract thermal spikes and back pressure changes. Sub-millimeter precision is never a static state. Rather, it is an active mathematically aggressive compensation against shifting physical realities. When properly tuned, a single digital command travels down the wire, forces its way through the magnetic hysteresis, calculates the exact pressure drop across the orifice, and stops 1,000 pounds of moving steel with microscopic exactness. We do not achieve this by eliminating friction, pressure drops, or thermal decay. We achieve it by building dynamic mathematical models that counteract those forces in milliseconds. But there is a hard physical limit to this mathematical compensation. Algorithmic loops cannot fix degraded hardware. To make the mathematics work, stringent physical maintenance is mandatory. Fluid contamination must be managed, filter life cycles must be tracked, and internal seals must hold their integrity. Maintenance provides the stable physical baseline. If the hardware degrades too far, the system's transfer function shifts beyond the algorithm's control limits, and the precision is lost. Mastering fluid power represents the ultimate convergence of advanced control.
Thanks for watching. Please visit the channel for more content and don't forget to subscribe and like if it was helpful. Comment if something is wrong.